Hello everyone, welcome to the ninth live interactive problem solving session for the course on concrete technology. I am Sedu Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, we'll start the session with an overview of the concepts that were covered in the lectures for week 9. So we had 4 lectures in this week 9, which had this module covered creep and shrinkage and also some other related properties. So in the first lecture, lecture number 27, so we looked at creep. So we were introduced to what creep is, right? So creep is the deformation that is seen in concrete because of sustained loading, right? So when you subject concrete to a constant load over time, it will deform, and this deformation is what we call as creep. So then we looked at what is the mechanism behind this creep, right? So what is the theory that explains this creep? And then we looked at how do we predict creep, right? So if we subject concrete to a certain loading, so after a period of time, say t, what will be the amount of deformation that we can expect, right? So how do we estimate that? So we looked at one method, which is the ACI method for the prediction of creep. And in the second lecture, lecture 28, so we continued with the prediction of creep. So here we looked at another method, which is the British method, right? So the previous one, the ACA method, is a little bit more comprehensive, right? And also it gives us an empirical equation. Whereas the British method, we saw that it is not as comprehensive as the ACA method, and it gives us certain graphs like nomograms for the prediction. And then we also looked at what are the different factors that affect creep and what is the effect of these different factors. And then we were also introduced to shrinkage in this lecture, right? So shrinkage again is related to deformation, right? So change in the dimensions. And also we looked at what are the different types of shrinkage, right? So we were introduced to different terminologies. And then in the third lecture, lecture 29, we looked into the mechanism of shrinkage, right? How shrinkage occurs, and also what are the different factors behind this shrinkage that we see in concrete, and also how do we predict shrinkage. So like how we had prediction of creep, so we also looked at how can we predict shrinkage of concrete. And in the final lecture of week 9, so we looked at the mechanism for creep, right? So we looked at some physiochemical processes behind the shrinkage, right? So in terms of the vapor pressures, and also the different mechanisms that explains shrinkage. And also we saw different methods that can be used for measuring the shrinkage, like the ring test, or the IS methods suggested method. And finally we concluded with thermal expansion, right? Again related to creep and shrinkage, right? So this is also related to the deformation, but because of the temperature effect. So we looked at that in the final lecture of week 9. Okay, so related to these concepts, we look at some questions now. So the first question is, which of the following will lead to increase in creep? So the options are increase in V by S ratio. Option B is decrease in the V by S ratio. Option C is increase in W by C ratio. Option D is decrease in W by C ratio. Okay, so the V by S is the volume to the surface area ratio. Okay, so as usual, we'll have polls for each question. So I'll create a poll now. Okay, this is a multiple answer question, so more than one option may be correct. Okay, the poll is launched. You can vote in the poll whenever you're ready. Okay, we have one vote for options B and C. Okay, we'll take a look at the answer. So the right options are both B and C. A decrease in the V by S ratio and an increase in the W by C ratio will result in increased creep. Right, so we saw this. So here the graph on the left shows the relative creep with the change in the relative creep with respect to the water to cement ratio. Right, so at about 0.65 or so, the creep at that water to cement ratio is taken as the baseline. So the creep at that, whatever is the creep we get for that water to cement ratio, is taken as 1, and relative to that we see what happens to the creep when the water to cement ratio changes. Right, so for values less than that, we see that the relative creep is less than 1, and for values greater than that particular value, like around 0.65, we see that the relative creep is greater than 1. So what we see is that as the water to cement ratio increases, the relative creep is increasing, right? So more water to cement ratio, higher will be the creep. And the second graph shows the ratio of the 30-year creep to the elastic strain, right? So basically this relates to how creep changes, like with respect to the deformation, right? So higher creep, this value will be higher in the y-axis, and the x-axis gives the volume to surface area ratio in mm, right? So again, we are given multiple graphs, each corresponds to different days of loading, right? From 7 days, 28 days, 90, and 1 year. And we see that for all at different ages, in all the different ages, we see that as the volume to surface area ratio increases, we see that the creep is actually reducing, right? So the question was about an increase in the creep, so which means that for the creep to be larger, the volume to surface area ratio has to be smaller, right? So therefore, the right options are a decrease in the V by S ratio and an increase in the W by C ratio will give higher creep, right? So those are the correct options. The question number 2 is, which of the following statements are correct? So the options are: creep is lower for lower relative humidity. Option B is creep is independent of temperature. Option C, creep is affected by the type of cement. And option D, creep decreases as the age at the application of load increases. Okay, again, this is a multiple options question, so more than one may be correct. Okay, the poll is launched. Any answers? Okay, we have one vote for options A and C. Okay, let's take a look at the answer now. So the right options are both C and D, right? So C is correct, but A is not correct. D is correct. Okay, so what is the question is, which of these are correct statements? Okay, so let's look at each of these. So creep is lower for lower relative humidity, right? So we have a graph here which explains what is the effect of relative humidity, right? So on the y-axis we have the creep, and on the x-axis we have the age or the time that has elapsed since the concrete was loaded, right? And we have different graphs, each corresponding to one relative humidity percentage, right? So we have for 50%, 70%, and 100%. Okay, so here we are looking at the effect of relative humidity, and what we are observing is if we take any particular age, right? So say let us say we take 90 days, and we see that when the relative humidity is 100, creep is lower compared to 70 and 50, right? So this is true at all the different time since loading, right? So you take any time. So for a higher relative humidity, we see that the creep is lower, and for a lower relative humidity, the creep is higher. Right? So therefore, the given statement in A is wrong, right? So it says the opposite. Creep is lower for lower relative humidity, right? So that is incorrect. So option B is creep is independent of temperature. So the graph on the right shows what is the relative creep for different temperatures. And again, we see that generally as the temperature increases, we see that the creep actually increases, right? So therefore, temperature does affect creep. So the given statement that creep is independent of temperature is not true. And option C says creep is affected by the type of cement. It is true because the type of cement affects the strength, right? And therefore, the strength will affect the creep or the deformation that we see in the concrete, right? Therefore, strength has a role to play, and therefore, this type of cement is a factor that affects creep. So C is correct. Option D says creep decreases as the age at the application of the load increases. Again, we go back to the graph on the left. So here we consider any one particular relative humidity, right? And then we look at what happens as the time since loading changes, right? So as the time becomes larger and larger, right? So we have sustained the load, we have kept the load for longer periods of time. So what happens at that time? The creep is actually increasing. So you keep the load, you sustain the load for a long period of time, you will see more and more creep, right? So that's what we are observing from this graph. But the right. Okay, so this is a different, this is not related to option D, right? So this says that creep decreases as the age at the application of load increases, right? So this is not not for how long the load is sustained, but at what point the load is introduced, right? So suppose so for example, you apply the load after 7 days versus you apply the load after 28 days, right? So that's how we compare it. So what happens after a long period of time? So your concrete compressive strength will increase, right? So with time, the strength of the concrete will increase, and therefore, the later you apply the load, what will happen is the creep that will be formed will be lower, right? So the early you apply the load, you will see large deformation. The later you apply the load, you will see lesser deformation, right? So therefore, that is a correct statement that creep decreases as the age at the application of load increases. So which means age at application of load means at what point after the hardening do you apply the load, right? After 7 days or 28 days or so on, right? So the later you apply, there will be lesser creep. So D is also correct. So out of the four, C and D are the right statements. Okay, so question number 3. So we have to match the following constants given in the column, in the second column, K1 to K5, to what these constants stand for. So for what conditions or for what factors do we have these different creep constants, right? So we have 5 constants given here, K1 to K5, and 5 different factors, which are the curing condition, relative humidity, volume to surface area ratio, slump of concrete, and the aggregate content. And so we have different matches given here, and now we have to match the constants to the correct factors. So this is for creep. Okay, so this is with respect to the ACA method. So we have these constants taken from the ACA method. So we have 4 matches. So you can take a moment to recall which factors or which constants are related to which factors, and then answer in the poll. Okay, the poll is live. Okay, we have a note for option C. Okay, let's take a look at the answer. The right option is C. So the match is given in the same order as it is given in the table, right? So A is matched to 1, B with 2, C with 3, D with 4, E with 5, right? So the right matching is in the order as it is given, right? So K1 is for the curing condition, K2 is for the relative humidity, K3 for the volume to surface area ratio, 4 for the slump of concrete, 5 for aggregate content, right? So this is the equation from the ACI method, right? So we have phi infinity of t 0. So what is this method for? This is for predicting the creep of concrete, where the phi infinity is nothing but the ultimate creep coefficient, right? So we have the ultimate creep coefficient. So when the concrete was loaded at a time t0, so, right? So this is what we saw in the previous question, right? So this is the age at which the loading is applied, right? So it is T naught at point T naught. So if we apply it at T naught and then we leave it for a long period of time, right? So infinity. So what will be the ultimate? What will be the creep coefficient at that point? So that is the ultimate creep coefficient. So this is given by this equation, 2.35 times the product of six different constants k1 to k6, right? So the sixth factor, which is not mentioned in the table, is related to the air content, right? So depending on the different factors, so the ultimate creep coefficient will be determined based on this equation. So this is the ACI method of predicting creep, right? So the right matching for this is given in option C. So question 4 is, aggregate has direct effect on the long-term deformations of concrete because dash. So the reasons, we have to pick the right reason. So the options are, low elastic modulus aggregate will produce a stiffer concrete that will have relatively higher resistance to deformation. Option B is, high elastic modulus aggregate will produce a stiffer concrete that will have relatively higher resistance to deformation. C is, high elastic modulus aggregate will produce stiffer concrete with relatively lower resistance to deformation, and D is, low elastic modulus aggregate will produce stiffer concrete with relatively lower resistance to deformation. We have one vote for option B. Okay, the right answer is also option B, that high elastic modulus aggregate will produce a stiffer concrete that will have a relatively higher resistance to deformation, right? So that is the right option. for the aggregate has a direct effect on the long-term deformation, and the effect is also this. So when the modulus of elasticity is higher for the aggregate, so the concrete will be stiffer, and then the deformation will be lower, right? So there will be higher resistance. So there will be lesser creep when you use high elastic modulus aggregate, right? So this graph also shows that, right? So we have we have the relative creep and for different types of aggregates, right? So we have from basalt, rounded quartz, all the way up to red sandstone. So they have different modulus of elasticities, so given in gigapascal in the x-axis. So what we see is that, so when the modulus of elasticity is higher, for example like basalt, so we see that the relative creep is much low, right? So compared to something like a red sandstone, which has a lower modulus of elasticity, you see that the creep is much higher, right? So we see that the modulus of elasticity of aggregate has an effect on the creep, right? So higher is the elasticity, lower will be the higher is the modulus of elasticity, lower will be the creep um, that will be seen, right? So therefore, option B is the right one, right? So when you have stronger aggregates, which is shown by this modulus of elasticity, it will take more load and it will also resist the deformation much more than aggregate with lower modulus of elasticity. So moving on to question number 5. Which of the following lead to the autogenous shrinkage of concrete? The options are water consumed in hydration. Option B is loss of water by evaporation from the surface. Option C is suction by dry concrete below. And option D is none of these. Any answers? We have one option for D. Okay. The right option is actually A. It is the water consumed in the hydration process. Okay, so we looked at different types of shrinkages. So like the drying shrinkage, chemical shrinkage, plastic shrinkage, and so on. So autogenous is one of it, right? So as per the definition, what is autogenous shrinkage? It is nothing but uh, it is a shrinkage that we see at a macroscopic level for a sealed specimen, right? So we when we talked about the mechanism of shrinkage, so we looked at it is because of the movement of water. But here in the case of autogenous shrinkage, we are looking at a sealed specimen, so which means that there is no interaction with the environment, right? So there is no evaporation or addition of water which is causing this shrinkage. It has to do with the internal processes, right? So what's happening inside the specimen, right? Because it is like a sealed specimen. So what happens then? So the water is consumed during the hydration process, right? So we know this. So water is required, and during the hydration process, water will be consumed, and because of this consumption, so there will be reduction in the water. So because of that, the at the macroscopic at the specimen level, we will see that there will be a reduction in the volume overall of the specimen, and therefore that causes a shrinkage of the concrete. So that is actually what we define as the autogenous shrinkage, right? So therefore the reason for that is the loss of water or the consumption of water in the hydration process, right? So the others are not related to the autogenous shrinkage. For example, B is for the drying shrinkage and so on, right? So therefore it is only the hydration process and the water consumed in it which leads to the autogenous shrinkage. So the right option is A. Okay, so question 6 is for a concrete mix, there are four type of aggregate to choose from. So assuming that the primary criteria is to prevent excessive shrinkage, which of the following aggregate would be most suitable? So we have four options giving four different aggregate types, A, B, C, and D, and each the modulus of elasticity of these aggregates are given here. For aggregate A, it is 108 gigapascal. For B, it is 112. For C, 92, and for D, it is 97. So the question is, if you want to prevent excessive shrinkage, which of these aggregate type will we choose? Okay, the poll is live. We have one option, one vote for option A. Okay, let's take a look at the answer. So the right option is not A but B, the aggregate B, which has 112 gigapascals. Right, so this is so here we are talking about preventing excessive shrinkage, and we already saw what is the effect of the aggregate type on creep, right? So it has a similar role. The aggregate type has a similar role to play for shrinkage as well, right? So here also we are talking about when we are talking about preventing shrinkage, we are talking about preventing deformation, right? So how do we resist deformation? So as we saw for creep, so the same is the effect we are seeing here for shrinkage as well. So here we have again different curves are shown for different types of um, aggregates. So the lower ones are stronger aggregates, and then the upper ones are relatively less stiffer aggregates, right? And what we see is that for this small, the ones with higher modulus of elasticities show less shrinkage, at any at different times. Uh, so so if our primary interest is to reduce the shrinkage, we should go for the ones with higher modulus of elasticity. And among the four types of aggregates, A, B, C, and D, so the one with the highest modulus of elasticity is B with 112 gigapascal, right? So therefore our choice would be to go with B if our only criteria is to prevent the excessive shrinkage, right? So purely based on that, we go with option B with this aggregate B. So moving on to question number 7. For a given paste content, with the increase in the water to cement ratio of concrete, we observe dash in shrinkage. So the options are increase, decrease, no change, none of these. Okay, one vote for option A, increase. Okay, so the right option is option A, increase. So it is. So when the paste content is fixed, but the water to cement ratio goes up, then shrinkage will be more, right? So that's what we are seeing here in this graph. So we have different water to cement ratios on the x-axis and shrinkage on the y-axis, and different curves are given for different volumetric content of aggregate. We can pick any one. The trend is the same. So what we see is that as the water to cement ratio increases, so we see that the shrinkage increases, right? So why is that? Because when you have a higher water to cement ratio, again, when the base content is fixed, which means that you have more water, the water content is higher. So when you have excess water, so what happens then, it is not really going to be completely used for the hydration. So you have too much water, so it will be in the capillary pores, right? So so what happens during drying, so all these excess water will be evaporated, and after the evaporation you will see that there will be a reduction in the volume, so which is going to increase your shrinkage, right? So therefore the right option is A, that shrinkage will increase when your water to cement ratio is higher. Okay, so moving on to question 8. Which of the following does not affect the coefficient of thermal expansion of concrete? So the options are A, modulus of elasticity of the aggregate, B, fraction volume of aggregate, C, grade of concrete, and D, moisture content. Any answer? Okay, we have one vote for option C. The right option is also option C, the grade of concrete. So here we are talking about thermal expansion of concrete, coefficient of thermal expansion. Right, so again, so we are looking at some of the similar properties. So so the effect of the modulus of elasticity of aggregate is same as what we saw for shrinkage and creep. right? So if you have higher modulus of elasticity, you'll see lesser thermal expansion, right? So because your stiffer aggregates will resist the expansion more, right? So you'll have better resistance. So similarly, when you have higher aggregate content, which is higher fraction volume, so again you will see that the expansion will be lesser because it is the paste which will experience more expansion relative to the aggregates. Therefore, you have higher content of aggregate. You will see that the overall thermal expansion of the concrete as a whole will be lesser. And option D, moisture content is also known to affect the thermal expansion, right? So at different moisture contents, so it is experimentally we have seen that it does affect the thermal coefficient of thermal expansion. But C is about the grade of concrete. So you have with different grades, you will get different strengths, but strength of the compressive strength is not really a factor that is affecting the coefficient of thermal expansion, right? So therefore, it is only C, grade of concrete, that is not really a factor which affects the coefficient of thermal expansion, right? So the right option is C. Okay, question 9, true or false? Higher aggregate content in concrete helps in reducing creep. So you have to say whether it is true or false. Okay, we have one vote for true. The right option is also option A, that the statement is true. So when we have higher aggregate content, we'll have lesser creep. So this graph shows that. So we have the graph showing for two different conditions, dry condition and wet condition. So when the aggregate is in dry condition and wet condition, and also when it is stored from the first day onwards, right? So for both conditions, what we are seeing is that, and the volumetric content of the aggregate in terms of percentage, so when it is higher, so here 0 is on the right side and then 100 is on the left. So when the content is higher, volumetric content, we see that creep is lower, right? So we see a clear trend in between the volumetric content and the creep, right? So therefore, the given statement that higher aggregate content helps in reducing creep is true. So when you have more aggregates, you'll see lesser creep. So the reason we saw earlier, because again this is for in at least in the normal strength concrete, the aggregates will have a higher modulus of elasticity, right, than the paste, so it will resist the deformations more. Question 10 is about the creep coefficient. So it is defined as a ratio of two quantities A and B. So ratio of A to B is given as the creep coefficient. So what are A and B? So you can use the chat to answer to this one. So what is creep coefficient? So what is the two quantities that are used in defining creep coefficient? Any answer? Okay, so maybe we can take a look at the answer. So creep coefficient is nothing but it is the ratio of specific creep to initial elastic strain, right? So that is the definition of the creep coefficient, right? So creep coefficient represented using the symbol phi, right? Phi of t comma t naught means it is the creep coefficient, for when the load is applied for a duration of t, t units of time after the time t0, right? So at t0 you apply a load and keep it for t duration. Then phi of t comma t0 is the creep coefficient for that condition. So it is nothing but the ratio of specific creep, so which is represented as c t comma t0 to the initial elastic strain epsilon naught, right? So that is the definition. So but what is the specific creep? Specific creep is nothing but the creep that you will experience when unit stress is applied, right? So if you apply stress of 1 unit, then whatever is the creep that you will see after t time units have elapsed from t0, that is given by the specific creep, right? So it is a ratio of this quantity to the initial elastic strain, right? So what is the initial elastic strain? So we have the strain versus time or age. So here T0 is the time at which you are applying the load, right? So when you apply the load, there will be so instantaneously there will be some strain that will be experienced, right? So and this is, let us say it is some epsilon naught or E naught, right? So this portion is the initial elastic strain. So what is this? So when you release the load at this point, so all the strain that is observed will be recovered, right? So it will again go back to zero. So that is the elastic part. But if you sustain this load, if you keep this load, then what you will see is that the strain will keep on increasing even though the stress is kept the same, right? So this increased strain or the increase in the strain at the same load, so that is by definition what we call as creep, right? So with time this creep will keep on increasing, right? So after some particular time t, so whatever is the creep that you have, so that is the total creep minus the initial elastic strain, so that will be your creep after some time t. So this is et minus e0. Et is this, e0 is here, so this difference will give you the creep and the ratio of this creep to this initial portion. So this epsilon naught or E naught, so the initial elastic strain, so that ratio is given as the creep coefficient, right? So one more point to be added is in all this in this experiment, so the stress is unit stress, right? So this load that we are applying is unit stress. Okay, only then it will be the creep that we observe, that the creep that we get will be the specific creep, and then divided by epsilon 0 or E0 will give us the creep coefficient. Okay, so the two quantities A and B are the specific creep and the initial elastic strain. Okay, question 11 is creep factor K2 increases with increase in relative humidity. We have to say whether the statement is true or false. So again, this is about the ACI method for predicting creep. So we looked at earlier the different factors. So K2 is it's with respect to the relative humidity. So what happens to the factor or the constant K2 when relative humidity increases? So does it also increase? Okay, we have one more for option A. Okay, so the right option is actually B, that this statement is false. So K2 will actually decrease when relative humidity increases. So we already saw what is the effect of relative humidity. So again on creep. So here we have creep versus the time since loading. But what we are interested in is that what is the effect of relative humidity. So at any given time, so for different relative humidity, so we have 50, 70 and 100 given here. So we see that lower is the relative humidity, then higher will be the creep, right? So which means that what is the equation that we saw, it was 2.35 times K1, K2 and so on, right? So if we keep all the other factors constant, then when relative humidity increases, what should happen? Our the predicted creep should be lower, right? So that is the effects, right? So if you have to predict it correctly, our K2, which is related to the relative humidity, should go down when relative humidity increases, right? So therefore, and also the equation, actual equation is 1.27 minus 0.006 H, where H is the relative humidity value. So you see the coefficient is negative for H. So when H is higher, this K2 value will go down, right? So that is from the equation you can say. But logically also it makes sense that K2 has to be smaller when relative humidity is higher, right? So because the creep has to be lower, right? So therefore the given statement that it increases with increase in relative humidity is false. Okay, so question number 12 is, in statically indeterminate structures, creep increases shrinkage, does not interfere with shrinkage in any way, reduces shrinkage, creep results in relaxation. Let me just recreate the poll because this is a multiple answer question. So maybe one or more options can be correct. So I'm just recreating the poll. Okay, the poll is launched again. So this is a multiple answer question. Okay, we have one more for options C and D. Okay, so the right options are both option C and option D, that the shrinkage will reduce and also creep results in relaxation. So right, so here we are talking about statically indeterminate structures. So in statically indeterminate structure, because of the restraint or the fixed supports, so what you will see is that there will be some restraint to the shrinkage, right? So there will be some restraint to the deformation that you will see, and because of that what you will see is that shrinkage will also reduce, and there will also be the relaxation effect, right? So both, because the deformation is resisted, both the shrinkage as well as the creep will reduce. So the right options are C and D. Okay, so question 13 is, a concrete mix has 50 MPa compressive strength at 28 days. At which of the following strength values is it most likely to exhibit secondary creep? So options are 25 MPa, 42 MPa, 33 MPa, and 12 MPa. Okay, we have one vote for option B, 42 MPa. Okay. But the right option is the option C, 33 MPa. Right? So why? Because we are talking about secondary creep, right? And what is secondary creep? So again, we have here strain versus time, right? So as we discussed earlier, so initially when you apply the load at some time t0, so there will be instantaneous elastic strain, right? So that is recoverable. But if you sustain the load, you will see increase in the strain for the given stress value, right? So that is what we said, it is creep. But there are also different stages for this creep. So when you when creep is developing, so the initial stage we will see that the rate of increase in strain will be actually reducing. So there will be a decrease, it will be increasing at a decreasing rate. So that is what we call as the primary creep stage. And then what we will see is the secondary creep stage where the rate is constant, right? So it will be linearly increasing with time. So that is called as the secondary creep stage. And then after some point of time, we will see that the rate of increase will be higher, right? So it will be increasing at an increasing rate, and then it will fail. So this is the third stage, or the tertiary creep stage, right? And so we are now interested in this middle portion, which is called as the secondary creep stage. And this secondary creep is usually observed at about zero point 0.6 to zero point 0.7 or 60 to 70% strength levels, right? So here we are looking at 50 MPa compressive strength at 28 days. So the secondary creep will be seen in this particular range, zero point 0.6 to zero point 0.7. So if you look at it, zero point 0.6 will be around 30 MPa and zero point 0.7 will be 35 MPa. So it is in that range, 30 to 35 MPa range. So the closest option out of the four for that is option C, 33 MPa, which is between 30 and 35. Right. So therefore, option C is the right option where we will be seeing the secondary creep. Okay, question 14 is dash is formed as a result of carbonation shrinkage. So what is the product because of the carbonation shrinkage? So I can use the chat to answer this one. What is the product formed in the carbonation shrinkage process? Any answers? Okay, we'll take a look at the answer now. So the product that is formed during the carbonation shrinkage is the calcium carbonate, right? So the reaction that actually happens is, so what happens is during the hydration process, the calcium hydroxide is produced, right? So we have a lot of calcium hydroxide that is produced because of hydration, the hydration reaction, and in the presence of an environment that is rich in carbon dioxide. So what happens is this carbon dioxide reacts with the calcium hydroxide that is produced, and it will result in calcium carbonate being produced along with water. So also even the water is produced, for this reaction to occur, the carbon dioxide has to be present, and also there should be moisture content. There should be enough moisture content that is available for this reaction to occur. But at the end of the reaction, you will see that calcium carbonate is produced, right? So that is the answer, that calcium carbonate is formed as the result of the carbonation shrinkage, right? So this is the carbonation shrinkage is one type of the different one of the different types that we looked at, right? But the mechanism for the carbonation shrinkage is slightly different than the other types, right? So while the other types, it was related to the movement of water uh, in within the concrete and movement of water in and out. Whereas in the carbonation shrinkage, it is really about the reaction with the carbon dioxide. So basically, it is like a attack or a carbon dioxide attack on the concrete, right? So in such an environment, you will see that this calcium carbonate being formed, and that results in a shrinkage volume reduction, and that is what we call as the carbonation shrinkage, right? So we have the drying shrinkage, which is the predominant one, so which is because of the evaporation loss of water, and this is carbonation shrinkage, this particular line, and the total shrinkage will be the sum of the two, the drying shrinkage as well as the carbonation shrinkage, right? So because the mechanisms are different, and these are different types, So the total shrinkage will be whatever is due to drying and whatever is because of the carbonation shrinkage, right? So that is the total shrinkage that you will see, and that is given by the solid line. Okay, so question number 15 is, which of the following is not a step in the mechanism of shrinkage? So the options are: A, it is a process related to capillary water; B, movement of interlayer water reduces the volume of CSH; option C is reduction in volume due to capillary compression to balance the capillary tension; and option D is fully reversible since no new bonds are formed in the process. So you have to say which of the following options are not correct or not involved in the uh, shrinkage mechanism. Again, this is a multiple option questions, multiple select questions, so more than one option may be correct. Okay, any answer? Okay, we have one vote for options C and D. So the right options are actually A and D. A and D are not related to shrinkage. So what is option A? It says that it is a process related to capillary water, right? So we are talking about shrinkage. So it's generally what shrinkage is because of. It's based on the adsorbed water or the interlayer water, right? So it's not from the capillary water, but the adsorbed water adsorbed to the surfaces, or the interlayer water, which is nothing but the gel water. So it's not a process related to capillary water. So A is incorrect. So B says it is the movement of interlayer water reducing the volume of CSH. This is true. So when there is the movement of interlayer water, what happens is some of the bonds that are formed will be broken, and therefore the volume of the CSH will come down, and that results in the shrinkage. So B is true. C says reduction in the volume due to capillary compression to balance the capillary tension. C is also true. The capillary tension so will also is one of the mechanisms that we saw that causes the reduction in the volume. So C is also a right mechanism, and D says it is fully reversible since no new bonds are formed in the process. So that is incorrect. So it is this shrinkage is not completely reversible. So it is we cannot just add the water that is lost and get back the same volume. So it is not it's not the case. So because there will be new bonds or actually be formed because of the movement of this water. So some are broken, but some new bonds are also formed, and therefore this process is not completely reversible, right? So it is not a fully reversible process because of the formation of additional bonds. So out of the four, options A and D are incorrect. So the question also asks which of the followings are not a step, right? So both A and D are incorrect, not part of the shrinkage mechanism. Okay, question 16 is with increase in the V by S volume to surface area ratio, the drying shrinkage dash increases, decreases, remains constant. Any answer? Okay, we have one vote for option B. Okay, so the right option is also B, is that it decreases. So when the effect of V by S ratio is that when V by S ratio increases, drying shrinkage will decrease. So that is true. So that is that we can see from this graph. So on the x-axis we have the V by S ratio in mm, and on the y-axis we have the ultimate shrinkage, right? And what we see is that for different types of aggregates, so we see that as the V by S ratio becomes larger, the ultimate shrinkage is actually going down, it is reducing. So larger is the V by S ratio, lesser will be the shrinkage, right? So therefore it has to, so the right option is B, that it will decrease, the drying shrinkage will decrease. But why is it correct? Because here we are talking about the volume to surface area ratio, right? So and also the drying shrinkage. So when will the volume to surface area ratio will be large? When the volume is large and the surface area is small, right? So in that case, this ratio will be large, right? So for drying shrinkage, what has to happen? So drying shrinkage by definition, so we learned that it is because of the loss of water by evaporation, right? So for evaporation to occur, so you have to have so for evaporation to be happening a lot, so you have to have a lot of surface area. So when the surface area is large, evaporation will be large, so loss of water will be large, so which will result in large shrinkage, right? But when this volume to surface area is large, it means that surface area is smaller. So with smaller surface area, evaporation will be lesser, and therefore shrinkage will also be lower, right? So that is why the higher V by S ratio is giving us lower shrinkage, right? So the right option is B, that shrinkage will decrease. Okay, so question 17 is moist concrete specimen exhibits lower compressive strength due to dash. So we can use the chat for this one. So what is the effect, or what is the term that we use to describe this condition that moist specimen is exhibiting a lower compressive strength? Any answer? Okay, so we'll take a look at the answer now. So answer is dilation. Okay, it's actually dilation. So what is dilation? So it's basically like the opposite of like shrinkage, right? It is the increase in the volume, right? So shrinkage, we said that it is because of the loss of water, right? So when drying occurs, we see shrinkage. So but the opposite of that is when moisture is being absorbed, we will see that it will actually swell. Concrete will actually swell, and this dilation. So what happens is that it will reduce your surface tension, right? So because of the adsorbed water, so the critical stresses are lowered, and that makes that fracturing uh, to be initiated from the pores, right? So because of this, you will see that the compressive strength going down, and this is what we call as dilation. So the increase in the volume or the swelling. Okay, so question 18 is, which of the following is not a factor affecting shrinkage of concrete? So the options are grade of concrete, aggregate proportions, relative humidity, proportion of cement in the mix, and workability of concrete. So which of these is not a factor affecting the shrinkage? Okay, we have one vote for option A, grade of concrete. So it is correct. So option A, grade of concrete, is actually not a factor that influences shrinkage. Right? So we looked at these different factors, so we know which are these. So the aggregate content or the aggregate proportions, the relative humidity, proportion of cement in the mix, workability, all of these affects the shrinkage, right? So we saw more aggregates or higher volumetric content. So we saw that shrinkage will go down. Again, we also saw the effect of relative humidity on shrinkage. Also, the proportion of cement in the mix is also one of the factors. So, because when you have higher proportion of cement, which means that your aggregate proportions will go down, right? And workability in terms of slump, again, we see that it also affects the shrinkage, the workability in terms of slump. So all of these factors are have an effect on the shrinkage, but it is the grade of concrete that is not a part of the factors that is affecting shrinkage. So it affects the creep, but it's not affecting the shrinkage. So grade of concrete is the right option. Question 19 is, creep of concrete is independent of temperature and relative humidity. So is this true or false? Okay, we have one vote for option B, false. Yeah, the right option is also B, false. So we saw that temperature and relative humidity are factors that affect creep, right? So therefore it is not independent. So we saw in particular that temperature, with increase in temperature, that creep increases, and also we saw the effect of relative humidity, right? So lower relative humidity will give you higher creep, right? So therefore both of these factors have an effect on creep. So therefore the right option is B, false. Okay, question 20. The volume of the hydration product is smaller than volume of unhydrated cement and water. This phenomenon is called dash. The options are A. Drying shrinkage, B. Chemical shrinkage, C. Plastic shrinkage, D. Autogenous shrinkage, and E. Carbonation shrinkage. Okay, any answer? Okay, we have one vote for option A. Okay, the right option is actually B, chemical shrinkage. So this is by definition. So the volume of the hydration product is smaller than the volume of unhydrated cement and water, right? So that is by definition is chemical shrinkage, right? So we already saw this, as in a related concept for the autogenous shrinkage, but at a microscopic level, when you look at it, so you initially you have the unhydrated cement and also water, right? So this is your initial volume. And what happens during hydration? Some of these cement will be reacting with water to form the hydration products, right? So the original volume, so the water is consumed from the original whatever was present, and then the hydration product is formed. The volume of this hydration product is lesser than the initial unhydrated cement volume plus the water that was consumed, right? So therefore the overall volume is going down, right? So because of that, because of this hydration reaction, the shrinkage that occurs is called as the chemical shrinkage, right? So the drying shrinkage is actually because of the loss of water by evaporation, right? So here it is loss because of the hydration process, which results in the formation of the hydration product whose volume is lower than the initial volume of the unhydrated cement and water, right? So by definition, that is what we call as the chemical shrinkage. Okay, so the right option is option B. Okay, question 21. Shrinkage of concrete is maximum in which of the following conditions? So the first one is low water to cement ratio and lower aggregate percentage. Option B, higher water to cement ratio and lower aggregate percentage. Option C, moderate water to cement ratio and high aggregate percentage. And D, high water to cement ratio and high aggregate percentage. Okay, we have one vote for B, high water to cement ratio and low aggregate percentage. So B is correct. Right, so here we are talking about maximum amount of shrinkage, right? So it will occur in this particular condition. So we looked at the effect of these two factors individually, the effect of water to cement ratio and also the effect of aggregate percentage individually. So here we have to pick out the right combination. So among the water to cement ratio, just among looking at the water to cement ratio among the different options, so we have to first find out whether low, high or moderate is the right one where we will see higher shrinkage. So again coming to this, so this graph shows both the effect of the volume of aggregate as well as the water to cement ratio. So as we saw earlier, as the water to cement ratio increases, you will see that shrinkage will also go up, right? So in for any particular volume of aggregate, so the effect is the same. So higher water to cement ratio results in higher shrinkage, right? So among the four, so it could be either B or D based on just the water to cement ratio alone. So that eliminates A and C. So the other one is the aggregate percentage. Again, what we see here is different curves for different volume of aggregates. So from 50% up to 80%. And what we are seeing is, so as we have higher and higher aggregate percentage, right? So take any water to cement ratio, let us take 0.5. So the larger aggregate volume will show a lesser shrinkage, right? So 80% aggregate will give a lower aggregate shrinkage compared to say 60%. So you have more aggregate percentage, there will be less shrinkage. So here we are talking about maximum shrinkage. So for maximum shrinkage, your aggregate percentage should be low, right? So among B and D, so B has the low aggregate percentage, right? So the right combination is high water to cement ratio and low aggregate percentage that will give you the maximum shrinkage. So the right option is B. Question 22. Which of the following below given option is not correctly matched about factors affecting creep? So in this table, we have the first column giving different factors affecting creep, and the effect of these factors is given in the second column, or the effect on creep. Right. So here, which of so each row is one match. So we have to say which of these is not rightly matched. Right. So the option is 1, 2, 3, and 4. Okay, we have an answer, option C. So the right option is option C, that the third matching is incorrect. Okay, so what are the matchings given? So it is so high water to cement ratio results in increased creep. So that is correct. So we already saw that. So high modulus of elasticity decreases creep. So this is also true. We saw that higher is the stiffness, so it will take more load and therefore it will restrain more. uh, the deformation will be restrained more, therefore creep decreases. So correct. So third matches low relative humidity decreases creep. So this is incorrect because we saw that low relative humidity will have higher creep, right? So the effect of relative humidity is that, so when relative humidity increases, your creep decreases, but at low relative humidity you will have higher creep. And the fourth is higher air content increases the creep. So this is also true. So when you have higher air content, you have more porosity. So which means that more, water can be occupying that pores, and then because of the drain, you will see that, or there will be lesser, strength because of that, so that will lead to higher creep. So that is also a right match. So it is only 3 that low relative humidity decreases the creep is wrong. So here is the graph that shows that effect of relative humidity. So again, lower relative humidity has a higher creep compared to a higher relative humidity, right? So therefore, the right option is option C, the matching 3. Okay, question 23. So we have two statements. So statement 1, high volume to surface area ratio of concrete will result into less creep. Statement 2 is evaporation on the surface of the concrete will be less due to high volume to surface area ratio of concrete. So less movement of water will take place in concrete. So we have to say which of the following option is true. Only statement 1 is correct, statement 2 is incorrect. B, only statement 2 is correct, statement 1 is incorrect. C, both statements are correct and statement 2 is the right explanation for 1. And D, both are correct, but statement 2 is not the right explanation for statement 1. Any answer? Okay, option C. Okay, so right option is also C, that both the statements are correct, and statement 2 is the right explanation of 1. Right, so here we are looking at the effect of volume to surface area ratio on creep, right? So we saw that when V by S ratio is high, there will be less creep. So the statement 1 is correct, the effect given is correct. Statement 2 is explaining why it is so. So we saw that the mechanism of creep is through the movement of water, movement of the interlayer water, right? So when there is less movement, there will be less creep. So if there has to be less movement, then so if the surface area of the concrete is less, then evaporation will be less. So the movement will be less, right? So that will result into lesser creep. But for that, the surface area has to be low. When the surface area is low, what will happen is the volume to surface area ratio will be high because surface area is in the denominator. So when the surface area is low, volume to surface area will be higher. Therefore, that will result into lesser creep, right? So lower surface area, lower evaporation, less movement and less creep. So that is correct. And so when lower surface area, the volume to surface area ratio is high. So all these, so the explanation and also the effect both are correct. So the right option is C, that both are correct and the explanation is also correct. Okay, question 24 is what is the effect of creep on columns? So the options are gradual transfer of load from the rebar to the concrete, increase in the load capacity of the column, gradual transfer of load from the concrete to the rebar, and decrease in the load capacity of the column. Okay, we have one vote for option C. C is the right answer, that there will be gradual transfer of load from the concrete to rebar. So here this is what is the consequence of creep, right? So what happens because of it? So on columns, so we see that when there is creep, what will happen is there will be deformation in the concrete, right? So concrete, there will be a higher strain, so its volume is going to reduce, and because of that, what will happen is the load that is coming onto the concrete will be going to the rebar, so not the other way around. So option A says it is from rebar to concrete. So that is not the case. So that will happen when the steel yields. So when steel starts yielding, at that time it will stop taking load, and then at that time there will be transfer of load to the concrete. But in the initial stage during the creep, so what will happen is there will be load transfer from the concrete to the rebar, right? So B says increase in the load capacity of the column, decrease in the load capacity. It does not affect, it's not the effect of creep is not on the load capacity, but is on the transfer of load. So from either concrete to rebar or rebar to concrete. So, but during creep, it will be from concrete to rebar, right? So the right option is C. Okay, question 25 is what is the impact of creep on the stress concentration in statically indeterminate structures? So the options are increases the stress concentration, reduces the stress concentration, no impact, and D is increases the horizontal movement. Okay, we have one vote for option B. Okay, so the right option is B, that it reduces stress concentration. And so we saw this for statically indeterminate structures. So what happens is because of the restraint, there will be reduction in the reduction in the creep, right? Because of this restraint to the deformation in the statically indeterminate structure. So what happens because of that? The creep relaxation occurs. So what happens in creep relaxation? Your stress concentration goes down, right? Because of the relaxation effect. So the right option is option B. Because of the relaxation, there will be stress reduction. So that is given in B. Okay, so moving on to question number 26 is finer cement leads to higher autogenous shrinkage. So the options are so true or false. So whether we have to say whether this statement is correct. Okay, we have one vote for option A. Option A is correct. The statement is true. So what is autogenous shrinkage? So we saw this already. So it is the macroscopic change or the reduction in the volume because of this hydration reaction. So it is mostly seen in high strength concrete, right? So when you have finer cement, what will happen is there will be the hydration. You'll have better hydration, right? So finer cement particles will give you better hydration, and better hydration means better or higher hydration means there will be higher autogenous shrinkage. The autogenous type of shrinkage will be seen, right? So because of this increased hydration reaction. Okay, so that is true when there is finer cement, right? So that is we already saw this. You'll have a higher surface area, so there'll be higher reaction. So faster reaction also can happen because of finer cement particles. So you'll see that higher autogenous shrinkage happening in concrete that is having a finer cement. So the statement is correct. Okay, question 27 is what are the different effects of shrinkage? So the options are cracks in thin section, additional moments in tall buildings, loss of pre-stress in pre-stressed member. Option D is all the above. Here we have one vote for option D, all the above. Okay, so the right option is option D, all the above. Right, so all these options A, B, and C are actually consequences of shrinkage. So because of shrinkage, we see cracks in thin sections, so that is correct. So because of the reduction in the volume, you will see that the cracks appear, and this is also true in thin sections. Option B is additional moments in tall buildings. So again, that is also true because of the shrinkage. The because of the change or the deformation, you'll see that additional moments are being created, and also in pre-stressed concrete, so there will be loss of pre-stress, right? So because of the change in again because of the change in volume, so the pre-stress will be lost. So all the options A, B, and C are actually the effects that is seen because of shrinkage, and therefore the right option is D, all the above. Okay, so that brings us to the end of this session. Okay, so this is the last question. So if you have any questions or doubts, you can ask. Otherwise, we can wind up the session for week 9 and then meet again next week. Do you have any questions? Thank you.